Hello, it's David from David's Avery Electrical Services Limited, and today we're talking about safe isolation. Why? Well, I've done a few YouTube videos now, and I'm going to be doing some soon on my electrical testing using my Metrel multifunctional tester. But I feel it would be remiss of me to move on to an important subject such as electrical testing without first talking about the importance of safe isolation. So yeah, it's not the most exciting of topics, but nonetheless it's an essential one. Now I'm going to be a bit wordy with this, so apologies, but I will summarise for you at the end. Now many a time I've been asked by a client whether how often I receive an electric shock. Their assumption being that it's a common occurrence in my line of work, par for the course if you will. Well, it isn't, and for good reason. The first shock you receive may well be your last. There are a number of factors which determine whether an electric shock will be fatal, including your body's electrical resistance to earth at the time. And that changes depending on sweat, air temperature, moisture conditions, clothing, footwear, the floor you're standing upon, and so on. Other factors are the size of the electrical current you're exposed to, the protective device in use on the circuit you're in contact with, where on your body you receive the shock, how long you're exposed to it for, how healthy you are, for example whether your ticker's in good nick or if it has any deficiencies or a pacemaker, whether it's an AC or DC shock, whether you can release yourself from those live parts, or if you have others around you who can assist you and turn off the power, etc. The point is, it's a lottery, and for those who play any lottery, you'll know that you're more likely to end up losing than winning. And with a shock, that doesn't necessarily mean outright death. A shock can leave you with a nasty burn injury, or cause you to fall from the structure or the ladder you may be on at the time, or it can cause you to jump back and to land awkwardly on equipment or obstacles. One way or another, it can leave you temporarily or permanently incapacitated, even if you do survive it. So nobody wants life-changing injuries, and seeing as receiving an electric shock can be so dangerous so quickly, we need to eliminate the risk of such from our working lives. After all, as electricians, we should be safe in the knowledge that we can attend a normal day at work without it leaving us dead or disabled in some kind of way. I mean, for anybody in any job, going to work reasonably satisfied that you'll return home at the end of your shift without having been killed or crippled, that's just a basic human right, right? So, going back to the question I'm often asked, yes, I have received a 230 volt AC electric shock, and yes, I am still here. Annoying though that may be for my wife and the inflated life insurance policy she probably has placed upon me. However, how have I survived? Well, dumb luck and nothing more. The first shock I remember receiving was as a kid when I stuck my finger into an open lamp holder to see if it was live. It was, and although I didn't sustain any burn injury or worse, things could have been very different, especially as that was in the 80s when devices such as RCDs weren't commonly installed to cut the power when kids do stupid things like touching live parts. In my professional life, the only shock I've received was when I ignored the cardinal rule of safe isolation, which is never to trust that someone else has cut off the juice when they say they have. You don't take anybody else's word for it, ever. You check for yourself, you're responsible for yourself, and you make damn sure that power cannot be inadvertently turned back on while you are the one up to your elbows in the wiring. It only takes about 50 milliamps of current to stop your heart, which is why an RCD installed for additional protection is rated at 30 milliamps, a value which should be safe. 50 milliamps is 0.05 amps, which is a tiny number. Many of your home's plug-in appliances here in the UK are commonly individually fused at 3 to 13 amps. Larger power items like your electric cooker may have a 20 to 32 amp breaker. Your electric shower may be a 40 to 50 amp circuit. That's 1,000 times the current that could stop your heart. A fuse or circuit breaker is only there to protect the wiring from being overloaded. It'll do nothing to directly protect you. If you grab live parts of any electrical appliance by the short and curlies when there is no RCD present, then by the time the fault current is raised high enough to blow the fuse or trip the breaker, assuming it ever does, you'll long since be dead, lying in your own piss and shit and smelling of fried bacon, and that's not how you want to present your surprised corpse to your loved ones, presumably, if indeed there is any good way to present your surprised corpse to your loved ones. So as an electrician, how can you avoid a messy death on the job? Well, anybody already working in the field will already know that safe isolation is the answer, and anybody on an apprenticeship or in college will have had that drilled into them from the very beginning, hopefully, as this is the first lesson taught to you from day one. It's about doing the job without dying, or without killing someone else, so yeah, it's important. Firstly though, a quick aside on working live. What's that, you ask? I thought this was about safe isolation, so you shouldn't be working live. Well, quite right, but there may be certain circumstances where the power needs to be on for fault diagnosis, or where it's not possible to isolate because it isn't reasonable. This is less likely in a domestic setting, but commercial, medical or IT scenarios may dictate that the juice has to remain flowing while certain work is undertaken. However, just because the situation dictates that the electricity must remain on, it must be no less safe for you to perform your work. Simply because cutting the power could be, say, a risk to a business, does not make it acceptable for that risk to be instead transferred to a maintenance electrician. That would be like saying, well look, we can't risk powering down the server farm as our online sales would it, but we can risk the maintenance electrician's life by keeping the supply alive while it's worked on. Well, cheers. Under the Electricity at Work regulations, Regulation 14 permits live working only if 3 caveats are met. Namely, A. It is unreasonable in all the circumstances for it to be dead, and B. It is reasonable in all the circumstances for that work to be carried out, and C. Suitable precautions have been taken to prevent injury. So, if you're out on a commercial site and the manager is insisting on live working, you must only agree to that if there is a robust case for not being able to power down, if there is a clear need for the work to go ahead at that time, and if applicable risk assessments, method statements and personal protective equipment have been provided to allow you to perform that work safely. Risk is risk, and you can never be 100% sure that you are completely free from danger when working on something that's live. But if you can identify the known dangers and manage the risk, then there is a good chance you'll get to go home for your dinner at the end of the shift. I should also say that live working, when permitted by EAWR Regulation 14, is for testing and diagnostic procedures. Regulation 14 goes on to say that it would not be reasonable for repair work to be undertaken on live equipment. But enough of my waffle. Let's start with safe isolation as applied in a simple single-phase situation. What I'm going to do here today is to simulate a basic request by a client for a change of socket faceplate on this radial socket circuit, which in my test environment here consists of this single socket outlet on a 16 amp breaker. So we're going to want to turn off the breaker to this circuit, and maybe even the RCD, which serves other circuits too. Now, when it comes to removing the power, you can't just pull the plug on your client. You'll get no thanks if you shut off the power to a business's server or if you interrupt your customer's cordless telephone call mid-chinwag. So the first thing to do is to obtain permission, or, if required, a permit to work before switching off the juice. If necessary, at this stage, also ensure any risk assessments or method statements have been prepared for the work. For most sparkers working in a domestic setting for themselves, the risk assessment and method statement may be mental procedures rather than formal ones. That is to say, you're not going to sit down and start writing these things out, but you'll look at the job, evaluate what the dangers are and how you'll approach the work, and decide whether your experience, training and level of competency is such that you're comfortable in taking it on without risk to you, your client or your surroundings. That permission for isolation of the supply needs to come from the client or from a site contacting authority, and may be verbal or written depending on the environment. Communication is important, so you must verify that anybody who will be affected by the loss of supply to a particular circuit or the installation as a whole is aware of what is happening and has taken appropriate measures, for example by shutting down their computer, securing alternative means of lighting, even having the opportunity of making themselves a cup of tea before the power goes down for however long. Now, as the electrician who will be potentially coming into direct contact with live wiring, you need to be satisfied that the equipment you're using to keep yourself alive is in good order. A non-contact voltage indicator such as this has no place in safe isolation. These things are merely a basic tool for indicating that a cable may be live. You certainly can't rely on one of these to prove that anything is de-energized. Similarly, and surprisingly perhaps, a multimeter or a multifunctional tester is also not valid for the job, at least not as far as your competent person's assessment is concerned, should you be going through one, and that's because it's too easy to select the wrong function and get a false result. Now, you need a dedicated GS38 compliant voltage indicator, which, if you're not familiar with GS38, can be downloaded from the HSE website here. A couple of key points of GS38 are that the probe tips are no greater than 4mm, with 2mm being preferable, and that there are finger guards to prevent you from slipping down the probe once you're pushing it into live parts. I've got a couple of GS38 compliant voltage indicators here, this Martindale one being an example of a plain and simple instrument for measuring up to 400 volts with no whistles and bells, but with rather nice spring-loaded probe ends that can be kept shrouded or can be the shroud can be retracted to expose the tips at the end if you prefer. Jolly good. Now I also have here a TIS 845. Similarly, you've got your finger guards there, your GS38 tips, and this particular tester is slightly different in that it has batteries installed which enable some additional functions. So besides a voltage indication, this time with up to 690 volts, it can also be used as a continuity tester or fuse checker, thanks to the batteries built within. It's also got a backlit display, an audible output as you heard, and an LCD readout with a built-in ohm meter function, so it can actually give me a resistance reading. Very nice. The GS38 tip covers can be removed on this for some extra pokey poke should you need to get them into some tight places. Now, neither of these indicators have an on-off switch, so they'll react immediately whenever a voltage is applied to their probe ends. For safety reasons on the TIS model, if the batteries are flat or missing, then it will still give an audible and visual warning of the presence of a voltage, albeit not a measured indication. Okay, so the first thing to do with your voltage indicator when you get it out on site is to inspect it for damage. And you know what, I'm sure you're thinking, yeah David, that's going to happen every time I take it out of the toolbox. Well, let me show you here my old Dialog voltage indicator. This was my go-to contact tester for 5 years. Then one day the probe cable just dropped out of the end, just like that, no warning, no problems using it until the day it fell apart. So wear and tear does take its toll, and if there are any signs of damage, especially if live parts are exposed through cracked casings or damaged wiring insulation, then it's time to replace it with something new. Before using your GS38 approved voltage indicator, you need to know that it actually works. I can see that my Dialog tester here has had its chips. However, how do I know that my Martindale or TIS testers are in working condition? Well, I have two methods at my disposal. The first being to try them on a known good supply. That is to say, on a working circuit before I pull the power, assuming I have a working source of supply, that is. And of course, I may be on a job where things aren't working at all, in which case I may be in stuck. So the other way is to use a proving unit. This Martindale proving unit takes a 9-volt PP3 battery and will put out 250 volts DC. So if I take my testers and plug them in, then it should prove, at least up to the 250 volt lights, that my tester is working okay. Let's just do that with the TIS one as well. And sure enough, there we go. So the lights light up to the 250 volt mark, and in the case of the TIS, it also gives me a visual readout on the LCD display. So the proving unit proves that my two testers are operational. So with my proving unit, we've proven that these two voltage indicators are in good working order, at least up to 250 volts. Jolly good show. Now, I've identified the circuit that I'm going to be working on, so I know which breaker it's on, and I've got permission to turn it off. However, if you're doing a competent person's assessment and you're demonstrating your knowledge of safe isolation to your assessor and you're at the consumer unit, then you must seek permission to turn off not just the circuit you're working on, but the whole consumer unit. So you turn off the individual circuits first to reduce the switching load on the main switch, and then the main switch goes off. The reason for that is because you'll probably find most manufacturers' instructions for consumer units state that the main switch should be off if the cover is removed. And of course, if you remove the cover without clicking off the main switch, then you're not following those manufacturers' instructions and therefore violating regulation 134.1.1 and potentially exposing live copper, which would be the case with my demonstration unit here, where there's no buzz bar cover over the buzz bar. So if you did that on a competent person's assessment, you might get told off for a big red cross against your name for that. Okay, so my consumer unit is off, it's isolated. Obviously we've still got power going into the main switch. Now I've already proven my voltage indicator is working, so if I use that now to test the output side of the main switch, then hopefully indeed it reads that it's dead. I'm getting no lights lighting up there. However, we've got no reading line to neutral on the output side of the switch, So the downstream circuit that I intend to work on should be safe. But how do I know that this thing is still working and that it truly is giving me an actual dead result and it's not a failure of the voltage indicator? Obviously we have just proven it, but maybe using it on the proving unit has caused a problem. Maybe it's blown a fuse within here or something like that. So once I've got my dead reading, I need to re-verify that my voltage indicator is actually still good. And we can do that by putting it back on the proving unit or onto a known good source of supply, such as in this case the input to my main switch, and we can see there that yes indeed my voltage indicator is still working. So when I put it on there and it says that it's dead, we know that it really is dead and that I won't end up dead by touching something that's live. Are you following this? So we prove, we test, and we prove again. While at the point of isolation, there's one other thing we need to do before we can begin work, and that's to lock off the circuit so that there's no chance it can be re-energised while we're on the job. In many cases, the point of isolation will be the fuse or circuit breaker position back at the consumer unit or distribution board as it is here, although there may be a more localised means of isolation, such as a double pole toggle switch, a pull cord isolator or a rotary isolator. These types of isolator may be located at the physical location where you're working, in which case locking them off is perhaps not so important, as it's not so easy for the supply to be re-energised by someone else without you noticing. But if the source of supply is remote, or if others are also working or are present on the same site, then it's important that the source of supply is locked off so that it cannot be re-energised without your specific knowledge and intervention. Obviously, if it's a rewirable fuse box, one of the older boxes, you can physically withdraw the fuse and put it in your pocket and take it away with you, and that should scupper most people from being able to get it back on again. But for a breaker board like this, we're going to need a physical lock-off device. Now, when it comes to lock-off devices, you'll find there's quite an array of them offered at horrendous prices out there. Most of my work is domestic, and I have to be honest, out of the pile of lock-off dongles I've got, there's only one that really does the biz for me. This one here will clamp onto pretty much any MCB or toggle isolator. It bites down with a grub screw and can be locked off with a padlock. I shall just demonstrate that here by locking off the circuit in question that we're playing with today. And there we go. Now, someone who is particularly determined may be able to wrench this off. But that's the case with many lock-off devices, and there's often little you can do to protect yourself against brute stupidity. So we apply the lock-off device and we also attach a sign before applying the lock itself. The sign I use here I got free from the IET stand at Alex. Alex is a great annual trade show for electricians. My local one is held at the Ricoh Arena in Coventry every September, although they go all around the country over the year. And I usually blow a ton of money on new tools and bits, but it's also a good place to pick up advice and updates from the tech talks and to see new innovations being displayed, and freebies like these laminated signs from the IET stand can also be picked up. Now, if you don't have a ready sign, then you can pick one up from your local electrical wholesaler or even just make your own. There's no standard text recognised by the wiring regulations for something like this, but you just need to state that the circuit has been deliberately locked off for maintenance and must not be powered back on. It also doesn't hurt to show a contact telephone number on there. On one site I also ran it through Google Translate to provide a Polish notice, because that site had Polish labourers who didn't speak the Queen's. So that's something to think about if you know you'll be working on a site where there's a language barrier. So I'm going to take my padlock, put it through the sign and put it through my lock-off device and click, there we go. Now obviously the padlock I'm using here requires a key, and of course there's little point in locking off the supply if you then go and leave the key where someone may use it without your knowledge. So you put the key in your pocket and keep it on you. You may of course choose to use a padlock with a combination, which is fine so long as you keep the combination memorised and don't blab it to others. So now I'm behind the socket at the point of the circuit that I actually want to be working on, and I'm pretty confident that the circuit is safe and locked off, but I'm not going to make any assumptions. So I'm going to use my voltage indicator to check between line and neutral, and sure enough I'm getting no lights there. It's indicating that it's dead. However, what if it's not dead? What if the line is still live and in fact the voltage indicator isn't showing anything because it's the neutral that's been disconnected? Maybe the neutral's broken, or maybe it's been wired incorrectly upstream and a single pole isolator has switched off the neutral instead of the line. In that sort of circumstance, the voltage indicator would indicate that it's safe when in fact it's not, and if I touch that I could get zapped. So when we're doing our voltage indication tests, we don't just do it between line and neutral, we also test between line and earth and between neutral and earth. and sure enough I'm getting no indication on any of my indicators there, but I've got to of course make sure that my voltage indicator is still operating, so I check it against a proven unit or a known good supply to make sure that it does indeed light up. So I can be reasonably confident here that all combinations of conductors are dead and that this circuit is safe to work on. So I should be able to proceed safe in the knowledge that I'm not going to die when I start work. One other thing to mention about applying your voltage indicators probes is to always place the first probe, often coloured black and labelled as the negative probe if your indicator supports DC, onto the non-line part of the circuit, i.e. the neutral or the earth, before placing the second probe, often coloured red and labelled as positive, onto the line or suspected live part of the circuit. Like this. The reason for that is that if we place this end of the probe onto the live part of the circuit, then the voltage will pass all the way through the indicator and all the way to the tip of the opposite probe. So this tip now has a voltage on it, which may itself be a shock risk if you do touch it. I can demonstrate that with my fluke here, which I've got set to volts, by keeping my voltage indicator onto the live part there, and by touching the end of the probe with my fluke's probe tip, and we can see we've got about 147 nearly volts, 147 volts floating on the end of this black probe when this red probe has been applied here. The actual voltage that you find on the end of the probe will depend on the resistance of the load. The load in this case being the electronics inside the indicator instrument itself. And the instrument of course may be fused or contain protection to prevent a shock from occurring if you do touch that. But I'm not about to test that theory for the purposes of this video. Suffice to say that when single phase testing, connect the black probe to the neutral or earth first and the red probe to the suspected live part under test, and you should avoid any nasty surprises. I've stated that in single phase applications we test line to neutral, line to earth and neutral to earth. In a three-phase environment there are 10 tests to perform, namely L1 to neutral, L2 to neutral, L3 to neutral, L1 to earth, L2 to earth, L3 to earth, L1 to L2, L1 to L3, L2 to L3 and neutral to earth. If all three phases have been isolated, then there should be no voltage readings in any of the above test combinations, but remember to verify your voltage testing instrument afterwards. Once the physical work is completed, you perform your appropriate dead tests, and if all pass, then you can remove your lock-off device and re-energise the circuit. To summarise then, plan what needs to be done and how you'll do it. Perform any necessary risk assessments or method statements and obtain a permit to work if required. Ensure you have the correct PPE and tools for the job. Obtain permission to isolate the power from someone in authority, in writing if necessary. Make sure the client is aware of how long power is likely to be removed for and what may be affected. Shut off the power at a suitable point of isolation. Lock off the isolation point to prevent accidental re-energisation and ensure the means to release the lock is kept about your person. Also post a warning notice. Examine your voltage indicator for signs of damage and for compliance with GS38 and prove correct operation. Use your voltage indicator to test all conductors for the circuit you're working on are dead. Recheck the operation of your voltage indicator to prove it is still functioning correctly. And begin work only when you are fully satisfied it is safe to do so. Remember, it's kill the power or kill yourself in this game. Cheers. Oh,